Okay, get ready because today we are diving into some seriously mind-bending stuff.
We're talking about geometry, but not the kind they taught us in school.
Yeah, forget triangles and squares. We're going way deeper than that.
We're talking about CPS geometry.
Have you heard of this?
It challenges literally everything we think we know
Really?
about points, lines, space, the whole shebang.
I've got to admit, even the name CPS Geometry sounds kind of intimidating.
Yeah, it's not exactly something you'd chat about over coffee, unless you're like a super math nerd.
But that's why we're here,
To
right?
break it down, make it understandable, maybe even have some fun with it.
Exactly. So where do we even begin with something like this?
Well, every geometry has to start somewhere. In the kind of geometry we're used to, that starting point is, well, a point.
Right, a point. Simple
Uh,
enough, right?
Seems simple, but it's actually where things start to get kind of weird.
How so? It's just a dot on a page, right?
Well, in traditional geometry, a point is defined as having no size, no shape, like it's not even really there.
Yeah, I remember that from school. Points are like the ultimate minimalist decoration, no size, no shape, no substance. But it always kind of bugged me. It's like, how can something be nothing but still be something?
Exactly. It's a paradox. And it gets even weirder when you start thinking about how points supposedly make up lines.
Right, because if a point doesn't have any size, how can you line up an infinite number of them to create something that does have length? A line.
That's the million-dollar question, isn't it? It's like saying if you add zero to itself enough times, eventually you'll get one. It just doesn't quite add up.
Okay, I'm starting to see why this CPS geometry thing might be onto something here. If the very foundation of traditional geometry, the point, is kind of shaky, then what does that mean for everything else built on top of it?
It's a good question, and it's one that CPS geometry tries to address head on.
So how does it do that? Does it just say, forget points, we're starting over?
In a way, yeah. Instead of these abstract dimensionless points, CPS geometry says, what if a point is something, but just on an incredibly small scale?
Okay, I'll bite. What if a point is something? What is it then?
What if, instead of being nothing, a point is actually an infinitesimally small sphere?
Hold on, did you say spheres?
Spheres.
Like tiny little balls?
Exactly. Tiny little spheres as the foundation of all geometry.
Whoa. Okay, that's a pretty big leap. My brain needs a minute to catch up. So instead of points being these abstract dots on a page, we're now talking about actual, even though they're unbelievably tiny, spheres.
You got.
And that's what CPS geometry is all about, building geometry on these tiny
It's a
spheres.
big part of it.
I have to admit, it's a pretty wild concept.
Mm.
But how do we even begin to wrap our heads around it? Where do we go from these tiny spheres? So we're not talking about just abstract dots on a page anymore. We're talking about actual, albeit unbelievably tiny, spheres. How does that even work?
It's a fascinating idea, isn't it? And it might sound strange at first, but there's a really compelling logic behind it.
Oh, I'm all ears. Convince me.
It goes back to the work of Gottfried Wilhelm Leibniz,
Leibniz, the calculus guy.
the one and only. He had this incredible insight while working with similar triangles.
Okay, similar triangles. I remember those. All the angles are the same and the sides are proportional, right?
Exactly. Now imagine you have two similar triangles, one huge and one so tiny it's almost impossible to see. Leibniz argued that even when these triangles become infinitesimally small, the ratios between their sides remain meaningful.
So even though the size is practically non-existent, the relationships within the shape are still there.
Precisely. It's not about the absolute size you see, it's about the proportions, the ratios that define the shape and how it relates to other shapes.
Okay, I think I'm starting to follow. So how does this relate back to our tiny spheres and CPS geometry?
Well, if the relationships between these infinitesimally small spheres, these points, are what truly define the geometry, then we can build an entire system based on them.
Instead of dismissing points as empty space, we're saying these tiny spheres are where it's at. They're the real foundation of geometry.
You got it.
Okay, I'm officially intrigued, but how do we go from these tiny spheres to lines, shapes, and everything else?
That's where things get really interesting. You see, Euclidean geometry doesn't specify how points are arranged.
Yeah.
They're just there. But CPS geometry takes a different approach.
So it's not just about replacing points with tiny spheres, it's about how those spheres relate to each other.
You're catching on quick. Think about what happens when you have a jar full of marbles.
They all clang together.
Well, yeah, but they also don't just sit randomly, do they?
Now that you mention it, no, they kind of settle into a pattern.
Exactly. They naturally settle into the most efficient, most tightly packed configuration. And that inherent packing order, that's a key principle in CPS geometry.
So you're saying that kind of close packing, as you call it, isn't just a coincidence. It's actually woven into the very fabric of space itself at the most fundamental level.
That's the beauty of this approach. In CPS geometry, space isn't just this empty canvas with random points scattered about. It has this inherent structure, this natural tendency to organize itself in the most efficient way possible.
Okay, I can kind of visualize that. But where do shapes come into all of this?
Well, those patterns that emerge from this close packing, they give rise to something quite fascinating, platonic solids.
Platonic solids. Those ring a bell, but I can't quite place them. Remind me what those are again.
Of course. Imagine perfectly symmetrical shapes, each one made up of identical faces.
Like a cube.
Exactly. A cube with its 6 squares, or a tetrahedron with its 4 triangles. These are platonic solids, and in CPS geometry, they emerge naturally from the close packing of those infinitesimal spheres.
Oh, right. Now that you mention it, I do remember those from geometry class. They were always so visually striking, almost hypnotic in their symmetry. But how do they connect to this idea of close packing?
Well, imagine those tiny spheres all packing together. Depending on how they arrange themselves, they naturally form the outlines of these platonic solids. They become the fundamental building blocks, the constructions of the system, much like the straight edge and compass are to Euclidean geometry.
Okay, so instead of starting with abstract points and drawing lines, CPS geometry says, let's see what happens when we let these tiny spheres organize themselves according to these natural packing rules. And boom, out pop these platonic solids, these beautifully symmetrical shapes that then become the basis for understanding this new geometric reality.
You're getting it. And
Yeah.
what's even more profound is that this principle of close packing, this inherent order at the smallest level, might actually extend to the universe as a whole.
Now, hold on a second. Are you saying that the entire universe might be structured according to the same principles that govern how a bunch of marbles settle in a jar? That's a pretty wild thought.
Yeah.
So if we're saying that the same kind of order we see in a jar of marbles, this close packing, might actually extend to the entire universe.
That's a pretty mind-blowing concept.
It really is. I mean, it's like saying the universe isn't just randomly thrown together, but it's organized according to these elegant geometric principles.
From the ground up.
Yeah, exactly.
Right.
So where do we even go from there? What are the implications of a universe built on these tiny spheres all packed together?
Well, for one thing, it could completely change how we approach physics.
Physics, huh?
Yeah,
I mean, I can see how geometry plays a role in physics, but this seems like a whole new level.
it really is. Because
Uh,
we're not just talking about shapes existing in space anymore.
It's more like space itself is shaped by these geometric principles.
Exactly. This source even mentions that in CPS geometry, lines and surfaces emerge naturally from the packing of these spheres.
So it's not just that shapes exist in space, but rather that space itself is inherently geometric.
We got it. Instead of space being this passive backdrop,
It's like this active participant.
right, and its very essence is shaped by these tiny fundamental units.
I like that, active participant, because it's not like we're just moving through an empty container.
It's more like the container itself.
It's made up of these tiny building blocks, all connected and influencing each other.
And those blocks, those spheres, they dictate the rules of the game, so to speak.
Okay, yeah, that analogy makes sense.
Yeah.
Because it's like, what's the difference between playing chess on a plain board
Right.
versus one where the squares themselves have their own unique properties, you know?
And who knows what new insights we might uncover when we start playing by those new rules.
Like in physics, you were saying.
Exactly, because physicists have been trying to figure out how to unify gravity with quantum mechanics, and maybe this new understanding of space provides some clues.
It's like this one geometric concept could unlock a whole new level of understanding about the universe.
It's definitely a possibility.
It makes you wonder what else we might be missing just by sticking to our old ways of thinking.
It's definitely a good reminder to stay open-minded.
Speaking of open-minded, this deep dive has really taken us on a journey.
We've covered a lot of ground, that's for sure.
We started with the simplest thing imaginable, a point.
And from there,
We've explored the very fabric of space, the nature of reality, and even the potential for new scientific breakthroughs.
it's amazing what you can uncover when you start questioning the things we often take for granted.
Absolutely. So for anyone listening who's feeling like their brain just got to work out, trust me, you're not alone.
It's definitely a lot to take in.
But it's also incredibly exciting to think about the possibilities that CPS geometry opens up. And hey, if you ever want to dive back into this world with me, You know where to find me.
I'm always up for a good deep dive.
Until next time.